The system of equations has a unique solution. Find the solution. X plus y plus 6z equals 3, x plus y plus 3z equals 3, and x plus 2y plus 4z equals 7. If we use an augmented matrix to represent this system of equations, then we would have the matrix 1, 1, 6, 3, 1, 1, 3, 3, 1, 2, 4, 7. This is an augmented matrix. We're allowed to perform a series of row operations such as multiply any equation or any row by a non-zero. We can interchange the position of any two rows. We can also multiply any equation or any row by a non-zero and add it to another equation or another row. We want to get rid of x in the second equation. To do that, we will take the first equation and subtract the second equation. In matrix form, we will take row 1 minus row 2. Technically, we would multiply equation 2 by -1 and add it to the first equation, but it is okay to take equation 1 minus equation 2. We obtain an equivalent system of equations. This is x plus y plus 6z equals 3. X minus x is now 0x, y minus y is now 0y, and 6z minus 3z is now 3z, and 3 minus 3 is now 0. To save a step, we can also take equation 3 minus equation 1, because we observe that if we take x minus x, the x will cancel out, to y minus y, then we only end up with 1y. So we end up with a new equation in this equivalent system of equation, which is x minus x is 0x, 2y minus y is 1y, 4z minus 6z is now negative 2z, and 7 minus 3 is positive 4, where we took equation 3 minus equation 1. In the matrix form, or in the augmented matrix, we will take equation 3, which is row 3, and we will subtract row 1. But this is the same as multiply row 1 by -1 and add to row 3. The equivalent augmented matrix is therefore 1, 1, 6, 3 in the first row, 0, 0, 3, 0 in the second row, 0, 1, -2, 4 in the third row. The goal is to transform this into a triangular matrix or a triangular system of equations. So we would interchange the second row with the third row, which is an operation that we're allowed to do. This is x plus y plus 6z equals 3, y minus 2z equals 4, and 3z equals 0, where we took row 2, or in this case equation 2, and we interchange it with equation 3. In the augmented matrix form, we took row 2 and we interchanged it with row 3. The new equivalent augmented matrix is 1, 1, 6, 3, where we took row 2 and bring it to row 3. So in row 3, we end up with 0, 0, 3, 0. And row 3 go to row 2. So this is 0, 1, -2, 4. On the left-hand side is the lower form, which states that 3z equals 0. If 3z equals 0, then z equals 0. And then we perform a back substitution. Y minus 2z equals 4. So y equals 4. Another back substitution, x plus y plus 6z equals 3. So x equals 3 minus 4, which is negative 1. The solution to the system of equation is an ordered triplet where x is negative 1, y is 4, and z is 0. From the augmented matrix, we also see that 3z equals 0, and so z equals 0. From the second row, we also see that this states that y minus 2z equals 4. So we'll get y equals 4 because z equals 0. And the first row states that 1x plus 1y plus 6z equals 3. And if we plug in z equals 0 and y equals 4, we will get x equals negative 1 as well. Going forward, if we are going to use matrices to solve the system of equations, we do not need to keep writing the system of equations. We only need to work on the augmented matrix by performing a series of rows operations.